This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Good morning. Welcome to the session on critical materials for energy technologies. This session will focus on many materials that once were unfamiliar outside the research lab. Things like selenium, lithium, platinum, rare earths. These are now essential to many of the renewable energy technologies. And if we hope to ramp up the mix of those renewables in our energy supply, we're going to need much larger quantities of them than we have historically produced. As a consequence, the question is, will they be available and at what price? And that's the question that these panelists are here to address. So let me first say a word about the speakers. You have more details in the bios in your program. The panelists will then have 10 minutes each to make initial remarks. After that, we'll take 15 minutes, during which I'll pose some questions to the panelists. And in the final 15 minutes, we'll open the discussion to questions from you, the audience. So our lead-off speaker on my right is Sang-Won Soo, who's a professor in the Bren School of Environmental Science and Management at the University of California here in Santa Barbara. His research focuses on the theoretical foundations and practical applications of life cycle analysis, tracing materials and their impacts from extraction through refinement, use, and eventual disposal. He's also currently a coordinating lead author of the 5th assessment report of the International Panel on Climate Change, which is due out, I believe, in October 2014?
Correct.
Okay. His topic is material implications for large-scale adoption of photovoltaic technologies. Next will be Tom Gradell, right here next to me, who's a professor of industrial ecology at Yale University. He literally wrote the book on his subject, Industrial Ecology and Sustainable Engineering. And he tells me that field is moving so fast he has to continually update his book. He's currently chairing a National Research Council committee that's looking at the linkages of sustainability in the federal government. That report is due out this summer. His topic is solar cell metals, a tale of oversupply and undersupply. Now on my left is Robert Jaffe, a professor of physics at at MIT. Best known for his work on quarks, confinement, and quantum chromodynamics. But he also has interest in energy on a more everyday scale, and has developed an undergraduate course on energy for the technically literate, which you can find at MIT. As a member of the American Physical Society's panel on public affairs, Dr. Jaffe led a 2011 study of by that panel of energy critical elements securing materials for emerging technologies. He will speak today on critical elements and terawatt scale deployment of photovoltaic power. And our final speaker on my far left is Alexander King, the director of Ames Laboratory. He's trained as a metallurgist and spent 18 years at the State University of New York in Stony Brook and 9 at Purdue before going to Ames Laboratory in 2008. And this spring, he's taking the helm of the newest of the 5 Department of Energy Innovation Hubs. And today he'll talk to us about that new hub, the Energy Innovation Hub for Critical Materials. Okay, so we'll turn now to Dr. Sue.
Can I just walk up to the podium?
Sure.
So good morning, everyone. It's my honor to be here to talk about some of the research that is going on this topic. So let me start with the climate change. I believe that there is no disagreement in this room that climate change is one of the greatest challenges that the humanity is facing today. And as Barbara mentioned in IPCC, we are working very hard to respond to the call for the 2-degree target demanded by the UNFCCC. And I can tell you that it seems to be very difficult to meet that target. And the challenge ahead of us really requires fundamental changes in the ways in which we supply and consume energy. And this graph shows one of the sustainable energy future that's painted by one of the international energy authorities, which is International Energy Agency. And what you can see here is that, well, by 2050, so it's not working, but I can tell you that not only the demand-side energy technologies, but also supply-side energy technologies need to reduce greenhouse gas emissions. So the bigger part on the bottom of this graph shows the amount of greenhouse gas emission need to be reduced by the energy supply technologies. That includes like CCS, carbon capture and storage, and also all kind of different renewable energy technologies. Thank you. So that is what I'm going to talk about, and I believe that previous speaker, Dr. McQuaid, emphasize on the demand-side technologies, which is very important. I mean, I will focus more on the supply-side technologies. So the scenario that the International Energy Agency was talking about is the blue map scenario. It's called blue map scenario. It's quite close to the 2-degree target scenarios by IPCC. And as you can see, the amount of energy that need to be produced by, for instance, renewable energy under the blue map scenario is really unprecedented. We are talking about several thousand terawatt-hour level of energy coming from renewable side. And there are some other projections or scenarios like IEA roadmap vision scenarios, and there are some industry forecasts. But in any case, the amount of energy coming from the renewable energy is really very, very significant, and that is something that we haven't seen so far. The question is, well, you can always build new scenarios and, increasing something 10 times, decreasing something 5 times. But the question is whether those sustainable futures that this International Energy Agency is painting in this scenario is something physically possible. It's materially possible. So that's what we are trying to test here. So this is the result of the report that we just have finished it, and it's currently under review. So unfortunately, I cannot show everything here, but I will give you kind of sneak preview of this report. This report is about the environmental and resource implications of renewable energy, and this is commissioned by the United Nations Environment Program. I'm part of the International Resource Panel. Actually, my colleague Tom is here, also part of the international panel. And we looked at the question of environmental impact and resource implications of large-scale deployment of renewable energy technologies. And we looked at the life cycle impact over 1,000 environmental exchanges, all kind of emissions and resources consumption. And we looked at the projections of materials efficiency improvements and conversion efficiency improvement. And we adopted a blue map scenario to look at the future of those energy supply technologies. And we reviewed around 30 electricity generation technologies, and we also looked at the mineral constraints for top 20 photovoltaics technologies. I can only show you a small part of the analysis. So this is one example, for instance, material requirements for CIGS, copper indium gallium selenide, which is one of the PV technologies. We see that a gradual reduction in the materials requirement into the future because our technology evolves, we need less materials to produce the same amount of photovoltaics capacity. So we take those kind of factors into account. And this is one of the results that I can show you. Photovoltaics in general, and also other renewable energy technologies that we have reviewed in general, produces less environmental and resources impact as compared to the current energy grid mix, electricity grid mix. So what is shown here is that the red line, dotted red line, is the amount of the environmental impact of current electricity grid mix. It is normalized as 100%. And these lines show the relative magnitude of environmental impact of CIGS, copper indium gallium selenide photovoltaics, as compared to the current average grid mix in the United States. And as you can see, in most cases, the CIGS generates much less environmental impact as compared to the average grid mix. But just there's one very important exception, which is metal depletion. So metal depletion is higher for CIGS as compared to the average electricity grid mix. So this is an important, it has an important implications for us, and whether this material depletion impact or materials constraint is an important constraint that impede the future deployment of larger scale application of photovoltaics or not. So we have similar results for other technologies, other photovoltaics technologies that is shown over here. So we tested this question for about 24 of photovoltaics technologies and see what if each individual technology over here generate the amount of electricity that is shown by the blue map scenario by 2050. How much of materials do we need in order to fulfill the amount of electricity required in order to meet the blue map scenario? And what is shown here is that, well, it depends really on the technology. Some technologies require a lot more materials than others. And what is shown here is the red line, 100% is the known reserve of that material, the constraining material by 2010. So the reserve is basically the amount of materials buried underneath the Earth crust that can be economically extractable, and more than 100% of that requirement. So if you require more than the amount of reserve based on current technology and known reserve, we cannot meet that materials requirement. But I say this with a caveat that the reserve number is not a fixed number. Many believe that it's fixed number. Actually, it's not a fixed number. It's a variable. It depends on the new geological findings and also new economics associated with the extraction technologies and also price of that material. So it is not unusual to see the reserve value doubles or triples or quadruples in the course of a short time period. Having said that, still, as you can see, if we are to meet the future renewable energy demand for photovoltaics using, which one this is a gallium arsenide, then we will need about 70 times more gallium than what current reserve is telling us. So this is important message here that, well, some of those scenarios are not really based on the physical reality in terms of the availability of those materials, and we have to consider this physical reality and materials availability in order to think about the larger scale deployment of those technologies. My last slide here is that, well, we tend to focus more on the panel itself, but one of the findings that we have reached was that not only the panels, but also the balance of system, which is the equipments and materials and bases, all those kind of things that are needed to support the panel, is also important driver for materials consumption. So what you can see here is that the copper needed for transformers, and steel for frames, transformers, and other materials used for balance of system for PV are very important drivers of material consumption. So these are the things that we also need to factor in. So I will just skip the conclusion. I think much of this will be discussed during the discussion, and I would like to just acknowledge two of my students here, they're sitting somewhere here, helped a lot to this research. Thank you.
So I would like to really make one central point in the remarks that I have, and that is that we know that metals are highly linked in technology. What we have not appreciated to the degree we should, I think, is that metals also have very strong but different links in geology. And this is likely to raise some interesting questions that basically have not been very well explored to this point. This is a diagram I call the flower garden of metals, and the idea here is that the metals shown in blue, copper, zinc, aluminum, and so forth, are the metals that we traditionally mine for. The copper mines, the zinc mines, and so forth. Each of these ores has within it small amounts, sometimes very small amounts, of the scarce metals that we tend to use in the more recent and higher level technologies, indium, gallium, selenium, and so forth. If we want indium, we must mine zinc, and then after we extract the zinc from those ores, we must further process the ores to recover the indium. If we want tellurium, we must mine copper, extract the copper, and then further process the residues to recover the tellurium. We don't have tellurium mines, we don't have indium mines. These are all companion metals that we get by mining the hosts. This diagram attempts to connect the most common photovoltaic solar power technologies with the ores that ultimately are involved in them. So we have near the top of the diagram crystalline silicon, amorphous silicon, cadmium telluride, and the CIGS solar cells. And below them, all the metals that are involved in the technologies, and below those, the ores that produce those metals. So depending on the technology you're interested in, you have connections to a number of different elements, and you have further connections to a number of different ore bodies. In fact, we're talking about 8 different ore bodies that are connected with photovoltaic power. And I'm showing this for energy, but you can imagine that we have a whole range of technologies in our modern world, and for those we use 60 or 70 elements in the periodic table, so this diagram could be considerably expanded were we to look beyond solar power and look at all of modern technology. And we would find it then connected to some 15 or 20 different common ore bodies, which not only is a diverse set, but is also a very diverse geographical set. So we get some of these ore bodies predominantly in some countries and on some continents, and others in other places. I want to make my point by looking particularly at zinc ores, which I've circled on the bottom, and then three of the companion metals for zinc ores, germanium, which is used in amorphous silicon cells, cadmium, which is used in the cadmium telluride cells, and indium used in the CIGS cells. If you want to make a lot of CIGS cells, you need to mine a lot of zinc in order to produce the indium. And one scenario you could imagine is a ramp up of CIGS cells requiring lots of indium. This would require mining lots of zinc. There are efficiencies connected with the extraction of indium, but basically the efficiency that zinc miners go for is the efficiency with which they can mine the zinc, because they don't make very much money on a very low concentration byproduct. So we could have a scenario here where we don't mine enough zinc to get the indium we want, because half of all zinc is used to galvanize steel. And if the building industry is not going strong, the zinc market demand is lower, not as much zinc is mined, and we have challenge with the indium. On the other hand, if we have a favorable situation where we really are getting all the indium we want, we may have a situation where we're mining more zinc than we need. And the consequence there is that the price of zinc would drop, and the incentive to recycle zinc products coming out of use would go down. There's another thing that shows up here, and that is that whether we like it or not, mining zinc produces cadmium. Cadmium is a toxic metal. If we are not using it in solar cells and other places to the extent that it's mined, we have to sequester it somewhere and keep track of it. So we have a linkage here between the companions of zinc and zinc itself, which relate to the demand for all of those metals, the degree to which they're interactive, and the degree to which our efficiencies are enabling us to get one or the other. The same situation, incidentally, holds for the tellurium used in cadmium telluride cells. Tellurium is a companion of copper, and if you mine copper, you also produce a byproduct of copper, arsenic, and arsenic, again, a toxic metal. So whether we like it or not, we mine copper, we extract arsenic, and then we have to figure out what to do with that. So my message here is that we haven't paid enough attention to the linkages that nature has forced upon us, and that this topic is not limited to the issue of solar power or electricity. It's one that applies throughout all of modern technology.
Well, let me begin by thanking the organizers for the invitation to speak here. My topic concerns a different perspective on the same questions that the previous two speakers addressed. Hopefully I'll be able to add a little to their point of view. What I'd like to speak about primarily is the question of critical materials constraints on deployment of photovoltaic power at a huge scale. If I have time, I'll comment on a couple of policy issues that were raised by the APS study that Barbara mentioned that I chaired. The work that I'm describing was done in connection with a study at the MIT Energy Initiative on the future of solar energy, which looked primarily at the question of whether solar power could shoulder a major fraction of the energy requirements or the electrical energy requirements in the mid to long-term future. What scale am I talking about? With the 20% capacity factor that solar power is burdened with, one has to multiply by 5 the produced power in order to get the deployed level. We're talking about the present time, annual growth rate of 250 gigawatts peak deployment per year in order to take account of the present expansion rate of electric power in the world. And by the middle of the century, that will rise to about 680 gigawatts peak per year. It's a huge number, but remember that power is going to come from somewhere. Of course, the criticality of a material depends very much on the kind of question you ask. If you're a company that's interested in producing and deploying solar power at a rate of tens of gigawatts per year, you're asking a very different question than if you're talking about deployment at the rate I just suggested of the order of a terawatt per year. In between, there's an order of magnitude of some kind of bridge to a sustainable future, which involves deployment at the level of hundreds of gigawatts per year. I'm going to primarily be talking about very large-scale deployment because the question we're interested in answering is whether this is a possibility for the world. The materials that we found that seem to provide the bottlenecks among the dominant and emerging technologies are the following. For crystalline and polycrystalline silicon, as you probably know, silicon's the most abundant solid element on the surface of the Earth, so that's likely not to be a critical element, but silver is. And for the two technologies that also share a fraction of the present deployment market, cadmium telluride and CIGS, involves four elements which were mentioned by both the previous speakers: tellurium, indium, gallium, and selenium. I'd just like to note before talking about these that the very important ingredient in the future of manufacturing of solar power is the economies of scale that are really key to lowering costs. And it's important to remember that the use of rare materials is, if anything, anti-correlated with scale. You can't save on these materials by the economies of scale. You just use more of them. The fundamental issues here are the underlying scarcity of these materials and the dilemma of co-production that Tom mentioned in his talk. Fundamental scarcity, it's important to notice that tellurium is down here at 1 part per billion in the Earth's crust, and several of the other elements, including indium, silver, and selenium, are below 0.1 part per million in average abundance. Co-production provides really serious issues for the long-term use of these materials. They're artificially cheap at the present time because they're byproducts. People get excited about them and invest in them because of their low cost, but they represent a roadblock to a sustainable delivery in the future. Really, the mapping of the problem that I'm describing can be summarized in this single graph, which in this case is for polycrystalline, the use of silver in polycrystalline PVs. Right now, about 10% of the world's new silver production is used in the inks and on the front to provide the front surface contacts in silicon PVs. That results in a cost of about 9 cents per watt peak. However, if one tries to scale that up to a high scale, one runs into trouble. What the graph shows is the total material requirement in tons on the vertical versus the deployment scenario on the horizontal. The curved lines on this log linear plot correspond to different choices of material intensity. At the present time, it requires approximately 64 tons of silver per deployed gigawatt of silicon PVs. That's the red curve, the red highest curve. So if you imagine deploying 1,000 gigawatts per year of silver, of silicon PVs using silver, you'd be needing 64,000 tons of silver, which is about 3 times the world's total production of new silver. There are plenty of other uses of silver. This is not going to happen. The good news is that the roadmap for the future development of silicon PVs anticipates a rapid reduction in the amount of silver. This is a graph that shows the silver usage on the vertical in grams per cell, and on the horizontal, it's the cell efficiency. The colored lines correspond to different material intensity in terms of grams, in terms of tons per peak gigawatt. By 2020, if this roadmap comes to fruition, the material intensity will be down below 10 tons per gigawatt, something like 2 tons per gigawatt. Going back to that graph, 2 tons per gigawatt is the lowest of those curves, the blue curve that runs along the bottom. The blue band in this picture is the present silver production, and you can see that a deployment of 1,000 gigawatts per year is within the capability of present silver production. The scenario is not so good for tellurium. This graph shows this roadmap for future tellurium intensity. The 2011 number is about 74 tons per gigawatt. The combination of increased efficiency and reduced thickness leads to a number around 18 tons per gigawatt at what's called full potential by this Colorado School of Mines group that did this study. If you compare that to present tellurium production, the situation certainly doesn't look good. The inset in this graph shows the production of tellurium as documented by the USGS. It's between 100 and 125 tons per year. A couple of special studies in 2008, 2011, shown in pink, estimated production quite a bit higher at the level of 400 tons per year. Those numbers are graphed in this material intensity graph along the bottom. They look like a thin blue and thin pink line. If you imagine deploying 100 gigawatts per year of CAD-TEL photovoltaics at the lowest material intensity, the aim of the roadmap, you would require using 2,000 tons of tellurium per year simply for CAD-TEL photovoltaics. That's at least 5 times higher than the highest present estimate of production, and assumes that all of the production would go into these photovoltaics. And that's 100 gigawatts per year. That's not a sustainable long-term future for PVs. There's some figures on what kind of production is available. The most optimistic scenarios get up to about 2,000 tons per year. Finally, there's a similar graph for CIGS. I think in the interest of time, I won't go into it in detail. The moral of the story is that CIGS lies somewhere in between, and that a deployment level of the order of hundreds of gigawatts per year is conceivable. So I'd like to switch now and just mention a couple of consequences from the policy study from 2011. I had the pleasure of working with a wonderful group of people on this, 2 of whom are over here on my left, Alex King and Tom Gradle. And the recommendations that came out of that study were for federal policy to try to address not the particular flavor of the month, what was a shortage then of rare earths, but instead the long-term question of stewardship of these unusual elements that are emerging all over the periodic table that play a significant role in new technologies. The recommendations were for coordination, information, research and development, and recycling. The recommendation for coordination was largely implemented by the OSTP, taking responsibility to coordinate federal activities. And the recommendation for research and development has begun with the siting of the new energy hub at Ames in Iowa, which is going to be discussed next. The other 2 recommendations are still out there. One of the most important is to increase the flow of information that would make it possible for people planning investments in these technologies and doing research in laboratories to make sensible investments in the future, knowing what kind of availability and what kind of obstructions they might face. So I think I'll stop there. Thank you.
Dr. King?
So the previous speakers have explained what the problem is, and I suppose it's my job to deliver a solution. Let me just say it's not easy. I used to think that thermodynamics was difficult, but of course I always told my students that at least if you understand thermodynamics, you know what's possible. Then I started talking to economists, and I realized that life is just a whole lot more difficult when you start thinking about economics, because thermodynamics might tell you what's possible, economics might tell you what's going to happen, and finance will tell you on what timescale it's going to happen. And it's timescale that I really want to get to in this discussion. So with that, let me see. Let me explain what the Critical Materials Institute is going to deliver. This is the 5th of 5 energy innovation hubs. These were the brainchild of Steve Chu. I have to say, a brilliant idea to bring together the best and brightest to solve well-defined problems in a short time frame. We have 5 years of funding, renewable for a second 5, but we have to show clear progress within 5 years. To put that 5 years in context, 2 of the things you can do to solve a material shortage are go out and find more material, that is fundamentally mine for more. It takes between 10 and 12 years to get a mine up and running once you know where the ore body is. So 10 to 12 year time frame doesn't fit well with our 5-year time frame. If you invent a substitute material, which is one of the other things we'll be trying to do, the track record is that it takes about 18 years to have a substitute material accepted and put in place in a product that is actually bought by anybody. So 10 years, 12 years to establish a mine, 18 years to establish substitute materials, 5 years of funding. What are we going to do? So here are the things that the Critical Materials Institute has promised to deliver. We're going to assure supply chains despite the timescale problems. We're going to address current critical materials issues, which means basically the critical materials identified in DOE's critical materials strategy, which are 5 of the rare earths and 2 other metals. We're going to address the need for technical talent. We have not trained people in the US in the areas of supply chains and the production of basic materials for about 30 years. And the people who know anything about that are rapidly retiring from the workforce. We need to replace before they're all gone. We will provide critical materials information to researchers, producers, OEMs, to the government too. And we will work to coordinate critical materials research around government agencies. We are not the only solution that the government is putting in place for critical materials. Critical Materials Institute is a hub. DOE has several ARPA-E projects, several basic science projects in the same area. The Department of Defense is ramping up very specific projects related to its own needs. Department of Commerce is coming on board very quickly, and we're going to try and coordinate all those things. So 4 outcomes. We refer to it as a 3D approach: diversify supply, develop substitutes, drive reuse, recycling, and manufacturing. Those are basically the pillars of the critical materials strategy as developed by the Department of Energy. There are a few other things you could think of doing to meet the demand for critical materials, but realistically, most of those involve manipulating the market, and we're not allowed to do that, so we won't go there. So we will be following the DOE critical materials strategy. One of the important aspects of what we're doing, though, is that we're being very selective about how we do it. There are, of course, 2 guiding principles, which boils down to very simple stuff, right? You've got 2 choices: produce more, use less. And between those, there's a whole bunch of steps along the entire so-called materials life cycle. So we study life cycles of the materials that we're working with very carefully. Life through death and beyond, obviously resurrection through the process of recycling, reuse, actually better than recycling even. Let me talk about a couple of very specific things that we can do. 4, 3, 2, 1, one integrated team among several different institutions. I could talk about why each of those institutions is involved, all the different strengths they bring, but the important thing we have within the Critical Materials Institute is a very good strength in economic analysis, very good strength in materials life cycle analysis, and the research ability to address whatever appears to be the most critical element in those areas. So let me just talk very quickly about a couple of things. Neodymium, this is used in high-performance magnets. I've seen a few earbuds around in the audience. I guess you're not listening. The earbuds use high-strength magnets to get high-strength lightweight. You find these magnets in all sorts of things, but the most prolific use has been in hard disk drive spindle motors. Some of the motors, the small motors you find in your cars, are things that drive the windows up and down, the things that make the mirrors adjust. If you have a high-end car, maybe the trunk lid latch has a lightweight motor in it. But generally small objects. The hard disk spindle drive motor uses about 3 to 4 grams of magnet, about 1/7 of which is neodymium. So very small amounts. The emerging uses, however, are big things. Traction motors for hybrid and all-electric vehicles. The Toyota Prius has a magnet in the motor that weighs about 20 pounds and contains about 7 pounds of neodymium. Wind turbines, which are popping up across the landscape, especially in Iowa, where I live now. A 2.5 megawatt wind turbine, if it uses a neodymium iron boron magnet, uses a magnet that weighs about 2 tons, 700 pounds of which is neodymium. What this is telling us is that demand, the things that are going to need neodymium are very big. The things that have previously used neodymium are very small. Without going into a great deal of analysis, what this tells you is that you cannot recycle your way out of the problem for neodymium. You have to mine your way out of the problem if you want to supply neodymium. And by the way, neodymium supplies tend today to be in fairly good balance. We're a little bit short supply of neodymium, but the way we are balancing neodymium supply is by throttling back use. So in this country, new wind turbine installations are only about 5% use of neodymium iron boron magnets. Those wind turbines are better than what we use as an alternative, which uses a lower strength, less high performance magnet, but uses a gearbox to increase the rotation rate of the generator. The gearbox is the weak link in the system. If you drive past a wind farm anywhere in the world, particularly in Iowa where they have hundreds of wind turbines, you will always see 1 or 2 of the wind turbines that are not turning while all the others are. That's not a power phasing operation on the part of the utility because the wind turbine is broken. What's broken usually is the gearbox, and the farmers on whose land the wind turbines sit do not allow the utility to come in during growing season. So that wind turbine is out of commission until after harvest. You can avoid all that if you have direct drive wind turbines. We do not have direct drive wind turbines simply because of availability. So we're being constrained today in the technologies that we can use by lack of neodymium, even though supply and demand look as though they're in balance. Okay? So what can we do on a short term? Starting a mine, like I said, takes about 12 years. Let me talk very quickly about froth flotation. This is really old technology. This is the industrial equivalent of blowing bubbles in your milk if you're 3 years old. What that does, if you've crumbled your Oreo cookie in the milk, is the Oreo cookie will float to the top on the bubbles. That's used in mining to separate ore from the other stuff, which you might refer to as just rock. Technically called gangue, which is a lovely word, I think. Froth flotation at rare earth mines concentrates bastnasite, which is one of the rare earth ores. It does not concentrate monazite because monazite does not attach to bubbles. Monazite contains more of the higher value rare earths, the heavy rare earths, but it currently goes into tailings heaps. On the flight out here yesterday, I flew over, I'm out of time, flew over the Mountain Pass mine, and you can see their tailings heap from 30,000 feet. It's a big source. It's sitting there on the surface. What we will be doing to try and solve that problem in a short term, rather than starting new mines, is go to existing mines where they have monazite in the tailings, put those tailings back through froth flotation if we can find a binder that will allow us to attach monazite to the bubbles in the froth flotation tank. What does that take? It takes quantum computation. You need the high-end computers that DOE has available that most mining operations wouldn't even think about accessing. So we'll be developing chemicals that will enable monazite to be collected in froth flotation. We think we can actually solve this problem within about 2 to 3 years and have additional resources coming from mines that are currently being worked. On an entirely different, they're going to stop me, entirely different basis, I could explain that mining will not get you out of the problem for terbium and europium, which are used in efficient lighting. The solution there is in recycling, and I could go into that later if we have questions on that.
Okay, thank you all. It was all very interesting. Let me start by asking about geopolitical constraints on the production of some of these materials. I think that's something none of you mentioned, but it's a factor in any case. So you want to start off, Sangwon?
Yeah, okay. Thank you, Barbara. So we talked a lot about the scarcity-driven supply constraint, but also there are enormous geopolitical constraint in supply side of those materials. As we all know that, rare earth elements, more than 97% of it is coming from only one country, it's coming from China. And whether China will keep on supplying rare earth elements to the United States depends on a lot of things. And that includes, for instance, how we get along with China in the future. And as you know, much of the rare earth elements are used not only for renewable energy, but also a lot of defense industry. So it really depends on how the situation between China and our allies will play out. And China has been imposing export tariff for rare earth elements, and last year they have increased the export tariff a significant amount and also reduced their export quota of rare earth elements. So it seems that there are increasing kind of protectionism going on some of the rare earth, some of the strategic elements that China has. But I would like to also look at this issue of geopolitical conflict in a little different angle. For instance, many of the manufacturers here, for instance, United Technologies, may be very well aware of the new SEC regulation about conflict minerals. And this is what a lot of many manufacturers in the United States are facing as a challenge. What it is that, Security Exchange Commission would like to impose a disclosure requirement for the materials that are coming from Democratic Republic of Congo and the 5 countries in the vicinity. And as some of the earlier speakers mentioned, we do not have any ways in which we can make those supply chain network through the global economy more visible. There is a lack of accountability and transparency in how the supply chain through the international trade are wired. So it is a huge challenge to the U.S. manufacturers. The reason why Security Exchange Commission is imposing this regulation is because there are huge civil conflict in Congo fueled by mining of cobalt and tantalum. And cobalt is almost exclusively coming from Central Africa, mainly from Congo. So geopolitical constraint and risk associated with them is not only about whether they will allow us to buy those materials, but also all the social and humanitarian cost associated with the mining, which is also huge. So I think there are different angles to be interjected in that question.
Okay. Anyone want to add to that? Alex? And then Tom, we'll get to you.
China is obviously high on the agenda and widely discussed these days because of rare earths. But in fact, it really is not important where the sources are. If you only have one source, you have a supply chain vulnerability. Sources can go offline for all sorts of reasons. Earthquakes happen, tsunamis happen. We're familiar with what happened in Zaire when it was Zaire before it was the Democratic Republic of Congo and caused the price shock of cobalt in '78. The real issue is fragility of supply. If you only have one supply, it almost doesn't matter where it is. It's worse if it's in a place that you don't have effective diplomatic relations with, but a single supply is still a bad idea no matter where it is.
Okay. Tom?
I wanted to really make the same point Alex did, but to do so with a few examples, because my experience in talking with people is they don't realize how many geographical regions technology involves these days. So almost all the world's niobium comes from Brazil. Most of the world's manganese comes from South Africa. A lot of the world's palladium, the bulk of it, comes from Russia. And China not only produces rare earths, but is a repository for the bulk of many other materials, including the tungsten that's used in tool steels and superalloys. So technology really depends on every continent on the planet.
You want to add anything, Bob?
Sure. I think it's important to realize that this is a generic problem of these materials, not a specific to the material that's important at the moment. This is really the fluctuation dominance of signals at low intensity. You have many, many sources of iron in the world, and you have few sources of platinum because platinum is far, far rarer. The problem tends to afflict primary production materials like platinum, where you mine the platinum directly, or niobium, more than it does co-production. So some of these very rare materials like tellurium found in copper throughout the world, and there are many deposits of copper. So that's one advantage of the relatively low level of production of in co-produced materials.
Mm-hmm. Okay. Next, I'll ask about the potential for recycling or reuse to alleviate some of the problems of supply. And I'll go first to Alex because he hinted he had more to say on that subject.
Yeah, well, very simply, if demand is growing because of the emergence of new technologies, so the world's demand for any particular element, such as neodymium, is going up because we're building wind turbines, each of which has 700 pounds of neodymium in it. The amount of material available for recycling is not enough to meet the demands for the emerging technologies. Worse, recycling neodymium is much, much harder than obtaining it from a primary ore. If you look at where neodymium is when it's being recycled, it's in a computer or it's in a smartphone, where it's manufactured along with 60 to 65 other elements, and it's very hard to strip it out in the recycling chain. If you go to a typical ore body, you've got the 17 rare earths that you're interested in, and oxygen, silicon, fluorine, carbon. It's a lot easier. We actually add entropy, as one distinguished thermodynamicist put it to me a few days ago. We add entropy in the manufacturing process that makes recycling hard. That notwithstanding, there are some cases for which recycling is the best approach. Fluorescent tubes, we already collect them because they contain mercury. So the environmental aspect of the fluorescent tubes has forced recycling. That means there's a resource there. The phosphors inside those things, which contain terbium and europium, are available. What's not been done yet is to find a way to regenerate the phosphors and remanufacture them so they can be reused. This is important because we expect the fluorescent tube business to decline after about 10 to 15 years. Hopefully LEDs will take over, be a much better idea, much better solution. We already have LED lights in here, which is good. So there's almost no sense in starting new mines for europium and terbium because they'll take, as I said, 10 to 12 years to start up. They'll come online just as the demand for terbium and europium is declining. So that case, the time constraints are telling us that recycling is definitely the right solution.
Any other comments on that topic? Yes, Bob?
Let me just add that the public consciousness of the issue of recycling critical materials is almost non-existent, that there has been an established consciousness of the need for energy efficiency promoted in many ways through the federal government's programs, but the need for a program both at an informal level and perhaps in terms of a specification of critical material content in devices would very much help to raise the awareness of these materials in the general population. And although not every problem can be solved by recycling, at least it creates a secondary stream that can help to even out fluctuations that are caused by problems with primary streams.
Okay, yes.
If you go to recyclers, they love outdated products. That's because this outdated old product, they tend to use materials in large quantity, more inefficiently. And the problem of new technologies that we are looking at and a higher material efficiency manufacturing is that we are using really tiny amount of those materials in each product, and that makes recycling very challenging and not very cost effective. So I think as our materials efficiency at the manufacturing phase increases, I think it will be increasingly more challenging to recycle them more effectively.
Any comment? Okay. When I read about this issue, or the more I hear about it, I'm struck by how complex it is. If you had as a goal to have your to increase the amount of renewables, and you want hence to increase the availability of some of these critical materials, you have to deal with the cost of extraction, the availability of mines that do extract, the geopolitical constraints, the environmental constraints. If your goal is to produce more renewables, where do you start addressing the problem to ease things? And in particular, if you were to give advice to policymakers, there's a retired one present, where would you start? Yes, Tom?
I think I would start by trying to talk with all the people who are designing new products. And I would take them down to the most advanced recycling facility in the vicinity and have them spend a few days there, and hope that they would come back with the idea that their design job didn't stop when they waved their beautiful product out the door and forgot about it. That it really involves design that enables and enhances the potential for recycling. Right now, there are almost no designers that think about this. They've never been trained with it, and they leave us with things that are much harder to recycle than they should be or could be, because it hasn't been part of their thinking.